Hi, Assalamualaikum. We are from Group 14. We'll present to you our CFD project with the title of Computational Fluid Dynamic Analysis to determine the downforce of motorcycle winglet. Okay, in this video, several main points that we will talk about is introduction of our project, our purpose, our goals, methodology of our project, analysis, and lastly, conclusion.
Aerodynamics is extremely important in motorcycle events for swimming purposes. However, such a particle design might result in the frontal lift while traveling at high speed. When the front wheel of a motorbike is raised and no longer touch the ground, this is known as frontal lift propellant. This, in turn, will result in a loss of front wheel traction, reducing overall motorcycle stability and control. A winglet is a bar attached to the motorcycle frontal similar to boost downforce or anti-lift. This downforce will aid in establishing enough traction on the motorcycle frontal area by keeping the front wheel in constant contact with the ground. All winglets were constructed and tested to serve as a preliminary motorbike benchmark for this investigation. A fastening mechanism will be used to attach this single flat winglet to the motorbike. The problem statement for our approach is the wing creates the downforce onto the motorbike. The size of wings for the bikes will affect the performance of the motorbike. The large wing will cause the pedestrian and the wings will hit the road or track. The 18 wings of the bike should restrict the size of the wings. Next, our goal is to determine and analyze the flow pattern and downforce generated by a motorcycle winglet. The downforce will aid in ensuring adequate traction on the motorcycle frontal section and optimize the design of motorcycle winglet that increase the downforce based on the result obtained.
The computer-aided design CAD model for the motorcycle winglet used in this study was created using the Autodesk Inventor Professional 222 and the Fusion 360 software. Two types of winglets have been simulated with different shapes. Type 1 winglet, the design follows the concept of aerodynamic, while the Type 2 winglet, the design does not follow the standard of aerodynamic concept. Next, ANSYS 222 software was used to carry out the design modeling, which is the motorcycle winglet. Generally, there are 5 analyses: geometry, mesh, setup, solution, and result. The first one, geometry. The box was sketched and extruded to form a wind tunnel for the winglet before the meshing process. Second is mesh. The wind tunnel's geometry has been selected for the best conforming method in tetrahedrons in the meshing process. The meshing configuration is then created using tunnel geometry, which has been chosen for the scoping method and the boundary scoping. Face sizing is selected and inflation mesh is created. Next, the name selection has been declared: the inlet, outlet, valve, and winglet. A section plan is created to observe the element and the winglet and wind tunnel nodes. Third, setup and solution. The viscous model in the fluid setup, the inlet was created for the velocity of 30 mm per second and pressure was set to 0 Pascal at the outlet. After that, the drag coefficient and the lift force were generated for the winglet before the calculation. The result has been calculated. The scale residual graph and drag coefficient was plotted. Lastly is the result. As a result of fluid flow, the plan has been created on the YZ axis. The contour and the streamline are also created to set with several variables such as pressure and velocity. The data was collected in the resulting process. The result was compared between two types of winglets.
For the analysis part, will consist of design winglet type 1 and type 2, downforce comparison, Reynolds number comparison, and independent test for drag coefficient. There are two types of winglet. For the type 1 designed in Air Force shape and type 2 designed in a non-Air Force shape.
We move for simulation ANSYS for winglet type 1. So firstly, our design winglet type 1 is a design that follows the aerodynamic structure. So in the simulation, we set the airflow from left to the right. So we can see that this is a 3D pressure control that occurs on our plane. But the value I will explain later. And then this is a 3D velocity streamline. So we can see that it follows our desired flow that we want. It's follow the structure design. You can see it's from left to the right. Next, we go to the pressure and velocity data that we get. So for the pressure, the minimum value that we get is around negative 192.34 Pascal. And for the maximum value that we get is 748.294 Pascal. And this velocity and simulation insists for type 1 winglet, which is the minimum value that we get is around negative 0.7787 meter per second. And the max value that we get is 42.9968 meter per second in the simulation. For the velocity simulation, we set it started with 30 meter per second, then we repeat with 40 and 50 meter per second to find the result.
As you can see, the simulation shows the pressure control at YZ plane and the velocity streamline indicates the airflow was from left to the right. For pressure and velocity type 2 winglet, in pressure control of the winglet type 2, it was apparent that the left top layer of the winglet had higher dynamic pressure gradient, which is 1852 Pascal, in contrast to the bottom layer, which recorded a lower dynamic pressure gradient, which is negative 2742.3 Pascal. For a velocity streamline of the winglet type 2, the left and the right side profile of the winglet had recorded a lower magnitude velocity gradient, which is 10.4252 meter per second on top and the bottom side, and had higher magnitude velocity gradient, which is 38.1343 meter per second.
Now, we move to downforce comparison. So after collect all the data from the NC software, then we plotted the graph. Then we got the average downforce for winglet type 1 is 60 Newton. Meanwhile, for the winglet 2, we got its average downforce is 0.61 Newton. You can see that the downforce produced by winglet 1 is much better compared to the winglet 2. This is because due to the shape of aerodynamic compared to design 2, this is a shape that does not follow the standard of aerodynamic shape.
Reynolds number is the ratio of inertial force to the viscous present in the liquid for flow over the flat plate. If Reynolds number is less than 5 times 10 to the power of 5, it is in laminar condition, while if the Reynolds number is more than the stated value, it is in turbulent condition. For winglet type 1, with 3 different values of velocity inlet, that is 30, 40, and 50 meter per second, we obtain a different value of Reynolds number. Then we know that it is turbulent flow in the winglet. Okay, for winglet type 2 with the same velocity inlet, we know that the flow in the winglet is also in turbulent condition.
The grid-independent test derived for each analysis target is listed in graph with parameter of drag coefficient. All the optimal mesh elements solved in NC Fluent software by mesh sizing range from 0 to 30 number of divisions. Therefore, the best parameter to select the mesh element in this study was the drag coefficient compared to lift force due to no rapid variation in the facet area average lift force value. The grid-independent test method was found to be appropriate at mesh element of 834,129, which is drag coefficient 0.4992. Result variation are not significant after the marked cell size, hence they will be considered as the better mesh size for calculation. This mesh will give the best result with less time as compared to the final mesh.
Okay, now the question is, which is the best choice between winglet type 1 and winglet type 2? Winglet type 1 is the best choice. Why? Because winglet type 1 was suitable for producing velocity and pressure at the top and bottom layer compared to design winglet type 2, produce more pressure but at the top left side of the winglet. Next, winglet type 1 produce higher average downforce that will aid in ensuring adequate traction on the motorcycle's frontal section. In conclusion, it can be understood that the design following the concept of aerodynamic, that is airfoil shape, is much better in reducing drag force, reverse flow, and wake turbulence, thus improving the streamline. That's all from us. Thank you.